All right, we're back. Short chapter, chapter 10, only two sections in this one. We'll split them up into 2 days, so 4 videos in this one. And we're going to be working on estimating a population mean in this first section. So we're going to go through some information along those. Your learning targets, of course, are there, some familiar things as you take a look there. And we're going to work on estimating that. So now, the formula for a confidence interval for a population proportion that we've used before, remember we have p hat with our critical value and then the standard deviation of the statistic is what we're looking at there. We can kind of adapt that just a little bit, and the interval is called a one sample z interval for a population mean. And so we're going to use that sample mean, and then of course that z-score, that's critical value, standard deviation on, as we've found that. And we've used that formula many times before, of course, with that population mean. So a lot of familiar things that we're putting together here. Unfortunately, if we don't know the true value of the mean, we rarely know the true value of the population standard deviation either. So, you can use the sample standard deviation as an estimate, but as you can kind of tell, things don't always work out as nicely as we'd like here. If we do Z with that, you can kind of see that we used a 99% confidence interval here, but only 92.5% of the 1,000 intervals actually captured it. So it's not doing what we want it to do, and that becomes a little bit of a problem. And to achieve a 99% capture rate, we're going to need to multiply by a larger critical value is what we're going to do. So the question is, what critical value should we use? Well, when we estimate the mean and standard deviation is unknown, we need to use a t critical value. All right, the critical value t has the same interpretation as z. It measures how many standard errors we need to extend from the point estimate to get the desired level of confidence. Now, we specify a particular t distribution by giving its degrees of freedom. All right, degrees of freedom is kind of what we're going to be looking at on this, a new little term that we're talking about here. All right, so let's take a look here. Now, what critical value t from table B, again on our little packet that we have, should be used in constructing a confidence interval for the population mean in each of the following settings? And again, we can do it with technology as well. So we'll show you tables. We also have that, that Tech Corner videos. So those are fantastic and posted in our online program to go ahead and take a look at those as well. We'll kind of show you that in class 2 as well. So an A, a 95% confidence interval based on a simple random sample of size 12. Again, the 0.025 because that's what's in each tail, right? And then, of course, our degrees of freedom is 11 that we have here, one less than our sample size. So we can kind of get that as our t-score. So that makes it kind of easy. Yeah, that's not so bad. Tables are good. How about a 90% confidence interval? Well, now we have 0.05 in each tail. And the problem that we have with the table is that, well, we just kind of go by tens here now. We didn't have it put in there. Now, the nice thing is with technology, what we're going to be able to do is we'll actually be able to use 47 as the degrees of freedom is what we'll be able to do there. All right, so again, the screenshot here, a little bit of what we'll do. Again, we'll walk through that in class as well as the video can show you. If you use the inverse t, 0.025 with the degrees of freedom 11, yeah, there's your t-score. If you do the inverse t of 0.05, and now here's where you can use that 47. Again, you can get to real specifics, so a little bit better with that technology, and I would encourage you to use that each time. All right, now again, conditions for estimating the population mean is that the random condition is crucial when doing inference. If the data doesn't come from a random sample, then you can't really do that. The 10% condition, again, remember that our sample has to be less than 10% of our population. And then the normal large sample condition, again, I think we kind of said we need to have a large sample. It has to be over 30 for that to work. So again, as we remind ourselves of all those wonderful things that we have to help us make sure that we have the right conditions to using that inference, we've got that right here. All right, so let's look at a problem here now. Determine if the large normal or large sample condition is met in each of the following settings. And to estimate the average GPA of students at your school, you randomly select 50 students. So right away, we can say, yeah, 50 is bigger than 30. Yeah, we're good. We're good. Okay. How much force does it take to pull wood apart? The stem plot shows the force required to pull a piece of Douglas fir apart for each of 20 randomly, oh, 20, we didn't kind of get to 30. And then, you know, if this would have been normal, we'd be okay if it looked normal, but it looks like we're a little skewed there, doesn't it? Yeah. So again, being, looks like it's skewed pretty strongly, skewed left. And then, of course, being 20 less than 30. And I'd probably say, no, we can't do that. Now, let's take a look at this one here. Now, suppose we want to estimate the mean SAT math score at a large high school. Here is a box plot of the SAT scores in a random sample. Now, the whisker looks like it might be a little skewed, but probably not too much. And because it is, yeah, and the 20 is not bigger than 30, but if it's only moderately with no outliers, yeah, we could probably pull it off in this case, make it work. So again, those kind of conditions. So if a question on the AP Stats exam asks you to construct and interpret a confidence interval, all the conditions should be met. Now you're still required to state the conditions and show evidence that they're met. So don't just don't bypass that. Make sure that you're putting that in. And if the sample size is small, if it's below that 30, then make sure you have a graph that shows that it's kind of approximately normal, and that should help you out. Okay, so that takes care of that first part of section 1. Until next time, I'm Mr. Boone.